Alright, so in this video we're going to be talking about waves in open pipes. And whenever I talk about a wave in an open pipe, what I mean is you got a pipe here and both ends of it are open. And how does sound resonate within that pipe naturally? So the first thing that we're going to talk about is, of course, the first harmonic. The first harmonic is the lowest frequency that this pipe will resonate at naturally. And what it's going to look like whenever you have the first harmonic with a pipe open at both ends, the sound wave is going to look kind of like this right here, where you have areas of high pressure at both ends, and then the sound's going to resonate out from there. Now, just for reference purposes, a complete wave looks like this right here, where you got the amplitude, crest, and back up over to equilibrium again. Now, if you look at this, it looks like we start off at the amplitude here and we end at a trough. So we end up having 2 quarters of a wave. So we end up having like a quarter left over here and a quarter left over here that we don't use. If we are missing 2 quarters of a wave, that means we have half of a wave. So on the first harmonic, the length of the tube is going to be equal to half of a wavelength. So it will be wavelength divided by 2. So that's what the first harmonic would look like. And remember, that is the fundamental frequency. And what would the second harmonic look like? So second harmonic, we'll draw our pipe here again. And what we're going to do is we're going to cram 2 fundamental frequencies in here. So that means we're going to have 2 half waves. So let's see here, we'll have a half wave like this. That's a half wave. And we'll draw another half wave like that. So those are both 2 half waves. And then we'll reflect it like so. And that's what the second harmonic would look like. You have the areas of high pressure at both ends. The tube is going to resonate out naturally. And since we have 2 half waves, that means we have a complete wave. So the length of the tube is going to be equal to 1 complete wavelength. We also know that because we go from crest down to trough and back to crest again. So crest to crest is one way to measure wavelength. And we also know that this is going to be twice the fundamental frequency. Let's go to the third harmonic, where we're going to have our pipe open at both ends. And we're going to put 3 fundamental frequencies in here. So we're going to put 3 half wavelengths. All right, so let's see if we can do this. We got 1 half of a wave, another half of a wave, and another half of a wave right there. And we'll reflect that. All right. And so what that means is we got 1 half, a second half, and then a third half. So the length of the tube is equal to, well, 1 wave and then another half, right? So that means we have 3 over 2 wavelengths. That equals to 1.5 wavelengths, right? Cool. Let's go to our fourth harmonic. This will be the last one we do. All right, so we'll say we still have the same length of the tube. That means we're going to stick 4 fundamental frequencies inside of this tube. I'm going to draw this bottom line a little bit better because I put a little bump in it by accident. So let's see if I do it better. Okay, we'll stick with that. So we'll put 4 fundamental frequencies in here. So let's see if we could do that. 1 half wave, 2 half waves, 3 half waves, 4 half waves, and then we'll just reflect it like this. All right, there we go. So this is what the fourth harmonic would look like. And oh, I forgot to tell you, on the third harmonic is 3 times the fundamental frequency. I'm sure you could have figured that out. But here we go on the fourth harmonic. Coming back here, we have one wave right there, and then a second wave. So if you just go halfway through the pipe, you have a complete wave. But the length of the pipe, it's now holding 2 complete waves. So that's going to be 2 lambda for the fourth harmonic. And this is also 4 times the fundamental frequency. So that's how you can visually represent, draw, and understand the wavelength of a wave going through an open-ended pipe. And you can figure out the frequency based off the fundamental frequency. You can also figure out the wavelength in relation to the length of the tube by saying the length of the tube is equal to how many wavelengths.